Okay, so this is a revision summary for atomic structure. Okay, so from the first bit here, electrons have a charge of -1. Protons, which are in the nucleus of an atom, have a charge of +1, and neutrons have a charge of 0. With the electrons, they are where I'm colouring in now with a highlighter. They're in energy levels or shells around the nucleus, orbiting. You can fit 2 in the first shell, 8 in the second, 8 in the third. The nucleus, which I'm highlighting in a different colour now, in the centre, the nucleus is where all the mass is, and the nucleus is made out of protons and neutrons. That nucleus takes up 1/10,000th of the size. So the mass is a tiny amount in the centre of an atom. And then another important thing, make sure you can recall and say how big an atom is. So the size of an atom is roughly 1 × 10 to the -10 meters. Okay. When electromagnetic radiation, so something like X-rays or gamma rays, sometimes ultraviolet, we've got all those from our waves and radiation topic in Physics 2 that you've now done. When electromagnetic radiation hits some atoms, the electrons can sometimes jump up a level, and then later on they fall back down to where they were. So that means some atoms can store that energy. The electrons jump up when radiation comes in, and when the electromagnetic waves, when it goes back down, it releases the electromagnetic radiation back out. So if we look at a certain atom, so for example, let's choose Na. On the periodic table, it's got the number 23 and 11. What does that tell us? Well, let me swap to the pen first. That tells us that there are 11 electrons. There are 11 protons. So 11 electrons that are negative and 11 protons that are positive. So that number at the bottom, the smaller number, is called the atomic number. It tells us how many protons there are, so it's sometimes called the proton number as well. And it tells us, because atoms are neutral, if it's got 11 protons, it's got 11 electrons. The top number is called the atomic mass. And that is added up. It's equal to the number of protons, which have a mass of 1, and neutrons that have a mass of 1. So in this case, I know that 23 equals, for sodium, 23 equals the 11 protons, that comes from down here, the small number, 11, plus, and then it's simple maths. What do I need to add to 11 to make up to the 23? And the answer is 12. So straight away, from these two numbers, these two, what I can identify is 11 protons, 11 electrons, 12 neutrons. You just take the bottom number away from the top to get the neutrons. And then we have a thing called isotopes. And what makes lithium here, Li, what makes lithium lithium? It's lithium because it has 3 protons. So on both of these two diagrams, left and right hand side, they both have 3 protons. That makes it lithium. However, when I look at the top number, on this side, 6 take away 3 is 3 neutrons. And on this side, 7 take away 3 is 4 neutrons. So these are 2 different isotopes of lithium. So they're the same in every way with protons and electrons, but they have a different number of neutrons. So when it asks you, if it does, what an isotope is, an isotope has the same number of protons, same number of electrons, and it has a different number of neutrons. So the difference, just try and link on your mind map the word isotope and neutrons, because it's the same atom. Both of these are lithiums, but they have different numbers of neutrons. Okay. How do ions form? Well, atoms have 2 choices. if an atom loses electrons, it sounds weird, but if you lose it, you become positive. So what we're saying is, this one on the outside here, and this one on the outside here, these could be given away when it bonds. If they're given away, it's no longer neutral. So what happened here with beryllium is it started off with 4 protons and 4 electrons. The 4 protons were each positive and the 4 electrons were each negative. When it's given 2 electrons away, it's still got 4 positive protons. It's now only got 2 negative electrons. Therefore, it has a charge of +2. So atoms can turn into ions when they lose electrons or when they gain them. So how did we get the model of the atom that we have today? Make sure you're not saying any of these are bad, because it was many scientists working together that gave us the model of the atom that we currently have. So it starts off with, around the 1900s, the idea that everything is made up of small little circles called spheres. The scientist behind that bit of work, who first named it, was called Dalton. And Dalton came up with the idea of everything's made of little circular particles called spheres. Then along came a scientist secondly called Thomson. And what Thomson said was, the plum pudding model, he suggested that there's a positive charge with negative electrons inside it. That's shown in the second diagram here that I've just circled. Then there was 3 other scientists. Along came a scientist called Rutherford, and he probably made the most influential discovery, because Rutherford suggested that from his experiments there's a nucleus and all of the material is in the nucleus, and the rest of the atom is full of empty space. So Rutherford is the one that came up with this idea. The idea that all of the mass of the atom is in the centre. Then came the next scientist. His name was, so there's 5 in order. His name was Niels Bohr. Just highlighted his name there. And he's the one who added the idea that electrons go around in shells around the nucleus. And then 20 years after this, James Chadwick came up with the idea that there's more mass in the nucleus, and therefore the idea that neutrons existed. He's the first one to mention neutrons as a new particle. So where we've got, I'll try and change colour just for a second, there you go, red. Where we've got Dalton, Thomson, Rutherford, Bohr and Chadwick, if you put their names, the D from Dalton, the T from Thomson, R, B and C, you can use the mnemonic don't for D, try, remembering, boring chemists, and it gives you the people's names in order. So it's remembering, it goes from a sphere to a plum pudding model to a nucleus model, and then the electrons added on, and then the neutrons. Rutherford's actual experiment, what did he do? Rutherford had a really thin piece of gold foil, only a couple of atoms thick. And because it's such an incredibly thin material, if Thomson had been right and its atoms were solid, when he beamed alpha radiation at it, so here, beaming alpha radiation in from this radiation source, when he beamed radiation at it, what should have happened was they should have all bounced back. However, what he showed was, change pen again, these lines here, nearly every atom, 99.9% of the alpha particles went straight through. a tiny number of particles were reflected when they hit the nucleus. So what Rutherford showed with this experiment was, if there's an atom, the mass is in a tiny bit in the centre. So just like this drawing, there's a tiny little bit here in the centre where the mass is. I'll just use the pointer. So there's a tiny bit there in the centre, that's where the mass is. And all of the rest of this, all of this here, that I'm shading in yellow, is empty space. So most of an atom is made of nothing. Then we need to move on to unstable atoms. If an atom is unstable, it can give out something here, and it can become more stable. And it can do this in several stages. These little bits that are given out are called radiation. And there's three types. We'll come on to those in a minute. Alpha, beta, and gamma. So we've got these alpha, beta, and gamma particles that can be given out, and the atom becomes more stable over time. The machine to measure that, and to measure, for example, here we've got this machine at the bottom, just highlighted in yellow, and it's measuring the radiation given out by this piece of rock. That's called a Geiger-Müller tube. And what it does is it detects when a piece of radiation hits it. So alpha radiation is a helium nucleus. And if you look at what's written here, it's got a +2 charge, so it's ionizing. Beta radiation is a much smaller particle, so it travels further, and it's a high-speed electron. A neutron splits up in the center of the nucleus into a proton, which stays in the nucleus, and an electron, which beams out. So therefore, because they're negatively charged, they are also ionizing. And then the third type is also on the electromagnetic spectrum, gamma radiation. Gamma is an electromagnetic wave, not a particle. It has no mass, no charge. However, it can disturb DNA, it can affect atoms when it hits them, so therefore it is also ionizing. Right, what do you need to know about alpha, beta, and gamma? First of all, make sure you know what can stop them. So alpha is stopped by a few sheets of paper, it's stopped by a few centimeters of air. Beta gets through paper, but any thin metal, so what we say is you can stop it with a very thin piece of aluminium, like aluminium foil. And gamma can only be slowed down, really, not really stopped if it's strong enough, but thick lead, really dense metal, or several meters of concrete. Down here, it tells you the speed. All three of them, though, are ionizing, which means they can damage living cells, and that could cause cancer. How do we show what happens in the nucleus? Well, here we have that mass number 238 and 92. If it gives out an alpha particle that I've just shaded yellow, we take 4 off the top, so that 234 and that 4 add up to the 238 over here, and at the bottom 92 ends up with 90 and 2. So what it's done is uranium, this one, has turned into thorium, and it's given out alpha radiation. With beta, a neutron turns into a proton and an electron. So the mass actually stays the same, because one neutron turns into a proton. That means the top number, 14, stays the same. However, the number of protons has gone up. So this started with 6 protons, ends with 7. And it gives out this fast moving electron, a beta particle. And with gamma, there's no change in mass, and there's the gamma. And gamma often happens at the same time as alpha or beta. When we take a radioactive substance, actually I don't need to draw it because it's shown there, just get the highlighter back. So this first diagram here, the time taken to lose half of your radiation for half of the atoms to become stable is called the half-life. And then it happens again, and then it happens again, because it's all probability. So for example here, it started with 100 radioactive units. To get down to 50 took this long. To get to 25, half of 50, will take the same amount of time. To get to 12.5 will take the same amount of time. To get to 6.25 will take the same amount of time. So we can use it for dating. We can date rocks, we can date skeletons, we can date wood, based upon how radioactive it is now compared to how it started. If I wanted to use this graph, if I found something which had this level of radiation, marked by purple on the line, then I could go down to here and say, okay, that is 2.5 half-lives. And if I know the half-life is 1,000 years, then that would be 2,500 years old. That's exactly the same here. We've got the count going down, and this is a radioactive sample. Here, for example, we can say, okay, the radiation is here, that means it's been there for 3 hours. Some isotopes are radioactive for thousands and thousands of years, and some just for minutes or seconds. And then the last bit is the difference between these two words. So these absolutely need to be on your mind map or index cards. Irradiation and contamination. The worst one of the two is contamination. Not that the other one is good. Irradiation means you are exposed to radiation. When you're exposed to radiation, there's a danger that it could cause harm to your cells when it passes through you or hits them. Contamination is when you actually touch, or it's on your clothes or shoes, you come into contact with an object that is radioactive. So when you walk away, you've still got that on you. Therefore the object can remain radioactive and you're receiving that dangerous radiation or passing it around to other people for a much longer time. So irradiation is dangerous, but as soon as you move away from it, you're fine. And contamination, the radioactive substance is on you and you're carrying it around with you. Okay.